So let's then look at a price process, at a stochastic process that is slightly closer to what we might realistically expect about stock prices, and also use that then to get some idea about what option prices will be, and that will culminate actually in the Black Scholes formula. So the intuition here is, rather than this constant linear growth that we just described in the previous part, in the previous video, stock prices are sort of more closer to being characterized by a constant expected return per year rather than a constant growth per year. So what does it mean, a constant expected return per year? That means that the change in the stock price as a proportion of this stock price itself, so ds divided by s, well, that's going to be proportional to time. So that's some growth rate mu times the change in time dt. So if you integrate this, actually what that boils down to is that this stock price which experiences constant returns per year will grow actually at an exponential growth. So it's constant growth rate, which means growth itself is exponential. So the stock price after a time t will be proportional to today's stock price, but then growing at an exponential speed with exponential growth rate mu. So stock value grows exponentially. Well, that's a nice model of stock prices, but of course not completely. That's not completely what we want, because we also know that stock values grow in an erratic way and have a random component as well. So what we do is we add to this and a piece of uncertainty, which we model again using this Wiener process. So in total, the returns ds over s of this stock are going to be described by this constant growth rate mu plus this erratic term, this stochastic term sigma times this Wiener process dz, this stochastic term. And again, this sigma measures the size of the uncertainty, or in other words, it's the standard deviation of the returns. It's called the volatility of this process. And this particular process has a name. It's called geometric Brownian motion. And so what does geometric Brownian motion look like? Well, here you see, well, the dotted line again would be the process without the stochastic part to it. So it would just be exponential growth, like you can see, from average behavior of stock price, or from perhaps from bank accounts. But lately, you will also know that that's basically how viruses expand in the society. So to that exponential growth, we add this stochastic term, this sigma dependent term, which also grows with s. So as the total stock price will grow large, also the fluctuations around this exponential path grow larger in a linear way. And together this process is geometric Brownian motion. So it's exponential growth with fluctuations, random fluctuations around that. And that's going to be, well, one of the simpler models of stock price, which is often used actually in reality. So if we have this particular geometric Brownian motion that this stock price is following, so what's then the probability distribution of the future stock price that will result from this motion from this evolution of stock prices? Well, if you know a little bit about differentiation, then perhaps you recognize ds over s, so the rate of growth of our stock price s. We can actually translate that pretty easily into the d log of s. And all the black terms here would be so what we would have if this were just a non-stochastic differential. There's a slight adaptation here. It's a red term minus a half sigma squared. That's a little technical change that we have to make, which basically accounts for the fact that this dz term, it had a standard deviation, so an expectation of dz squared, which was actually also proportional to dt. So that's it's technically this is called the Ito rule that I've used here, and that's something actually you'll learn about when you take the derivatives course in your master's class in derivatives. So this is geometric Brownian motion. So instead of saying that the ds over s follows this linear Brownian motion, we can also say the log of s follows this slightly changed linear motion with this mu minus a half times the volatility squared in the linear part. And what it means actually is that the logarithm of the stock price at a time capital T after today is going to be normally distributed. Well, how? Well, it will have a mean which has shifted by this drift term, the mu minus a half sigma squared times the amount of time that we have waited. But there's also again this stochastic motion around this, so there's some uncertainty around this. So we don't know exactly what the log of this stock price is going to be, but we know that's distributed around this mean with particular standard deviation, and that standard deviation is actually growing with the square root again of this time. So the standard deviation is going to be sigma times the square root of this capital T. So the logarithm of the stock price, according to this process, the change in the logarithm of the stock price is going to be normally distributed with this particular growing mean in time, and also the standard deviation which grows with the square root of time. So if that's true, then the stock price itself is going to be called log normally distributed. So we're interested actually in the log normal distribution for the stock price S. So what does that look like? Well, here's a graph of a log normal distribution. So it looks a little bit like the normal distribution, but first of all, it's only positive, right? Only has values over the positive side rather than the normal distribution, which stretches out in both directions, and it's a bit skewed, as you can see. So this is a typical picture of a log normal distribution. So this distribution basically maps out under this geometrical Brownian motion the future distribution of stock prices. So we don't know exactly what they will be, but this distribution is going to give us a probabilistic statistical view of where do we expect this stock price to lie in future periods. So well, that brings us to option prices. So if we know now what how this stock price itself evolves, well, if it evolves according to this geometrical Brownian motion, then we know indeed that the logarithm of the natural logarithm of this stock price will be normally distribution. It will also be normally distributed with some standard deviation of sigma square root of t. And again, this stock price itself will then be log normally distributed. So let's have a look then at an option. Let's have a look at payoff of a call option. So at maturity, so at time t, so when we have the right to buy, the right but not the obligation to buy the stock, well, what do we get? Well, if the stock price at that moment, so at time capital T, so as at time capital T, if that's above the strike price, the exercise price K, then we get, in a sense, we make a profit. Our payoff will be the difference, right? So if you remember the previous graph, where the strike price equal to 60, well, if the stock price happens to be 70 at that moment in time, well, what we gain is, of course, 70 minus 60 or 10. But if at that point in time the stock price S happens to be below the strike price of 60, K equals 60, then we do not get minus 10, but we can say, well, we are not going to use this call option, we just get 0. So this payoff is just the maximum of this stock price minus K, if that's positive, or 0 if S minus K at that point in time is going to be negative. So this is the payoff. So that's the payoff at maturity. So can we now say something about what we think the payoff or the price, basically, of the value of a call option today is before maturity? Well, what turns out to be the case is that the value of a call option is going to be the expected value of that payoff. Well, not just the expected value, but the discounted expected value, like we always do in finance, obviously. If you get something at a later date, we have to discount this, taking into account the fact that we could have put the money in an interest rate account and got an interest on it. So you have to take the present value, essentially, the discounted value of the expected value of that payoff. So the value of a European call option, C, as a function of today's price S, is going to be, well, the expected value, which is bold E, over here. The expected value of the payoff, or what was the payoff? Well, it was the maximum of the price of the stock at this maturity minus the exercise price K, or 0 if this S minus K at that point in time happens to be negative, because then we won't use the option. So the expected value of the payoff, but we do have to discount it, and this e to the power minus RT, that's essentially the discount factor, the present value factor. So you might know this as 1 divided by 1 plus r, so then 1 divided by 1 plus r to the power t, that would be discrete discount factor in continuous time, which I'm using here actually, so where we are using the to be precise, we're using continuously compounded interest here. We write this as e to the power minus RT. So this value of a call option is going to be the expected value of the payoff. So expected value of this thing over here is the payoff. This E is the expected value, and this first bit here, e to the minus RT, means we're taking the present value of that. So we're discounting this with the interest rate R, and taking into account here that this value is only coming in after t years of time. So the one subtlety here again, which I'm not actually going to explain, but it's not you might have noticed this little twiddle above the E. So this twiddle actually denotes the fact that this expectation actually goes for a slightly corrected so-called risk neutral process. So that's some technicality again that we need to take into account for making sure that we can hedge this call option by having some continuous trading approach. Again, something that you'll learn when you take your derivative course. So what it boils down to is that instead of having the drift mu for this process, we're not going to use that drift itself, but actually we're going to replace that in this geometric Brownian motion by the interest rate rather than mu itself. So that's something that you'll learn if you take further courses in derivatives. So what does it mean when we do option pricing for Black Scholes? Well, if we indeed use this geometric Brownian motion for the stock price, it means again that the logarithm of the stock price in the future will be normally distributed with a mean, well, the current logarithm of the stock price today as 0, plus this drift part, now r minus a half sigma squared times change in time. So as time gets bigger, as the maturity is larger, this factor is typically getting bigger as long as r is larger than a half sigma squared. So it's growing. So the mean of this process is growing with time. But there's also going to be a standard deviation of uncertainty essentially around this mean. And again, this uncertainty is measured by the sigma factor, which measures the volatility and the amount, the magnitude of the uncertainty, times the square root actually of the time to maturity capital T. So if that's what the stock price itself is described by this log-normal distribution, then the value of a call is then actually the discounted value of the expected payoff of this call. So what is that discounted value of this expected payoff? It consists of two parts. So here we can see basically these two parts at work. So let's focus first on the red part over here. We see a minus K, which was this strike price, and this red bit N of some D2, which I'll explain in a bit, is going to denote the probability that actually S, the stock price at time T, is going to be bigger than the exercise price K. And remember, this is a call option, so as long as S is going to be bigger than the exercise price, then we're going to exercise this option and we're going to pay the strike price K in order to get this stock, because then it's going to be profitable. So this N of D2 is going to be the probability that indeed we're going to exercise this call option. So what's then the blue bit? The blue bit is the expected value of S itself, the stock price at that moment, provided that the stock price is going to be bigger than K. So what you see here is the expected value of S minus K, provided that S minus K is bigger than 0, which is what we had on the previous slide. So provided that S is bigger than K, well, that happens with the probability N D2. Just take this as a notation here. Well, in that case, we pay K, but what we get is the expected value of S in that case, which is the blue part here. So this builds up basically what the Black Scholes formula is that you undoubtedly have seen before. For instance, actually in the notebook that we are working from in the Python course. So what are these letters here? Basically, the notation here. Well, this big N is actually the cumulative standard normal distribution. So that's the integral basically under the bell curve, if you wish. And these D1s and D1 and D2, they are made up of the different parameters that we have. So they're made up of the stock price today, the K, the strike price of this option, this interest rate R, and then with the first part, D1, will have a plus sign here times, so plus a half times sigma squared times T. And the second bit, the D2, which occurs over here, will actually have the minus sign over here. And we have to divide this thing by sigma squared of T. So this is actually basically not something that we can go into detail into here, or want to go into detail into here. But this is actually basically the interpretation of the Black Scholes formula, which is this thing then here, Black Scholes formula for the price of a call option. And there's a similar expression, a similar formula, Black Scholes formula for the price of a put option. It's with the different D1s and D2s essentially interchanged almost. So that was the video on the stock price process and the Black Scholes formula. So that's as warming up basically for finding the option pricing methods that we're going to look at in this course, which will be numerical approaches to finding prices of options.